Hey guys, today we're going to be talking about the Heisenberg uncertainty principle. We're going to start off with a joke. So, one day, Heisenberg gets pulled over for speeding. The cop comes up to his window. "Do you have any idea how fast you were going?" "No," Heisenberg replies, "but I know exactly where I am." The cop, confused, carries on. "Well, you were going 25 over the speed limit." "Great. Now I have no idea where I am." While this joke doesn't explain the principle of Heisenberg uncertainty very well, it does introduce it at the most basic level. The Heisenberg uncertainty principle states that there are limits to how certain we can be when we are measuring both the position and momentum of an object, specifically a particle. Hopefully this video will be able to explain the Heisenberg uncertainty principle and its implications in physics. Before we can jump into the Heisenberg uncertainty principle, we need to discuss the particle-wave duality of electrons. This principle was first studied by Louis de Broglie. He learned that photons and electrons act as both a particle and a wave. This graph shows the diffraction pattern that electrons take when they are scattered on a certain surface. In taking measurements of positions of electrons, as seen in this figure, you can see that electrons are found in specific areas. Each particle is in a different location than the others, but it stays within a certain area. The locations of all these particles, when condensed into a line, shows a wave-like distribution. This wave-like nature of electrons was introduced by de Broglie and showed that distribution of all particles can be somewhat predicted based on the particle's diffraction pattern and wavelength, but that, ultimately, you can't predict exactly where a specific particle will end up or how fast it will get there. This led to Heisenberg's study of probability distribution. Heisenberg's studies led him to conclude that there was a limit to how much you could know about the position and momentum of an electron. He called this limit uncertainty. There are two types of uncertainty in Heisenberg's equations. The first is uncertainty in position, which is represented by delta x. Because an electron acts as a wave, the electron's position will be spread out if its location is measured multiple times. This means that the value of delta x, or the uncertainty of the electron's position, is approximately equal to the wavelength of the particle. The second uncertainty that comes into Heisenberg's uncertainty principle is that of momentum, or delta p. In order to find out where an electron is, you need to change its momentum via collision with some sort of detector. This collision will cause an electron to lose momentum to the detector. Since we can't tell how much of the electron's momentum was transferred to the detector, there is uncertainty in momentum. Uncertainty of momentum is represented by delta p, which equals h, which is Planck's constant, divided by lambda, which is the wavelength. Based on these equations, we can reason that decreasing wavelength, or lambda, would mean that delta x, uncertainty of position, also decreases. However, a shorter wavelength would mean a greater delta p, meaning there is more uncertainty as to the momentum of the electron. These two equations can be condensed into one equation, where uncertainty is in position times uncertainty in momentum is approximately Planck's constant. Furthermore, this shows that the two uncertainties are inversely related. As we become more certain of an electron's position, we are less certain about its momentum, and vice versa. Heisenberg went on to further his equation, stating that uncertainty of position times uncertainty of momentum is greater than or equal to Planck's constant divided by 4 pi. This equation is known as the Heisenberg uncertainty principle. This equation shows that we can, with a small enough wavelength, get close to knowing the position of an electron around an atom, but we will be unsure of its momentum. Overall, the purpose of the Heisenberg uncertainty principle is to show that it is impossible to perfectly measure the momentum and position of a particle. The closer you get to measuring the momentum, the less you will know about the particle's position. The more you know about the particle's position, the farther you are from being able to measure its momentum. How does this principle apply today? Well, one application of this principle will be one that most students in this class will experience in general chemistry. The use of Heisenberg's uncertainty principle has led to measurements of probability distributions for electrons, which has led to discussions of electron clouds and things like sigma and pi orbitals of atoms, where electrons are likely to be found. Now you know who to thank for making you learn the very exciting concepts surrounding molecular orbitals and their effects in atomic bonding.